All right, so now we'll look at summation formulas. Again, something you probably have seen before, but maybe you forgot it, and I want to make sure you've seen a solid justification of why these things are what they are. So summation formulas for arithmetic sequence starts with a question like this. What is the sum of the first 1,000 numbers? There's all kinds of stories about how this came up and how people put Carl Friedrich Gauss as like the guy who we don't know how authentic all those stories are, but there's lots of nifty stories. Anyway, so this means, what is 1 plus 2 plus 3 plus, etc., all the way up to 998 plus 999 plus 1,000. So do you know a way that you could do that in 5 minutes? Or you could do that. You can add up all those numbers in less than a minute, actually, if you know what you're doing. In less than a minute. Do you know how to do it? All right, well, I'll tell you how to do it. Maybe some of you do know how to do it. So basically, you look at pairs of numbers that go first and last. So, what's 1 plus 1,000? It's 1,001. What's 2 plus 999? It's 1,001. What's 3 plus 998? It's 1,001. So you're going to have a bunch of 1,001s. And the only question is, how many of them are you going to have? Well, you're going from both ends. The numbers go up to 1,000, so you're going to have 500 pairs. So you have 500 pairs of 1,001. So you just do 500 times 1,001, which equals 500,500. Right? Less than a minute. Add up all the numbers from 1 to 1,000. All right? Now, so you can generalize this idea. So what are we doing here? We're adding the first and last numbers. So how would I know for any given sequence of numbers what the magic pair is always going to be? It's the first number plus the last number, whatever that is. So that's a sub 1 plus a sub n. And then I'm going to multiply that by the number of pairs are there. Well, how many pairs are there? If I'm adding up n numbers, then it's going to be n over 2. Half of those. All right. So this is one formula for the sum of an arithmetic sequence. So this is for an arithmetic sequence only. All of this depended on the fact that this is an arithmetic sequence, right? 1, 2, 3, up to 1,000. All right. That's arithmetic with a sub 1 equals 1 and d equals 1. So kind of a special case. But it turns out that that case, you can try it with different sequences. It works for any sequence of numbers, this process. Even, by the way, if the number of terms is odd, the one that you have left over in the middle is always going to be exactly half the value of all the pairs that you had. So the n over 2 times the sum still works. All right. So it's pretty remarkable. Anyway, this form of the equation is not terribly useful because you have to figure out what that last term is before you can use it. So we like another version of this where if we take our formula here for arithmetic sequence, a sub n is a1 plus n minus 1d. And we just plug that in to the a sub 1 here. So that equals n over 2 times a1 plus a1 plus n minus 1d, right? That's basically just replacing the a sub n with this expression for a sub n that we have for arithmetic sequences. So then you get n over 2 times 2a sub 1, combining the two like terms there, n minus 1d. And then it's just a matter of, how do you like to rearrange this? I like n times a sub 1 plus n minus 1d over 2. That's how I like it. But, so arithmetic sequences are not going to turn out to be as exciting to us as geometric sequences. So we're not going to use this one terribly a lot. But if we do, this is the form that we're going to use for the summation formula for arithmetic sequence. All right, so this is the summation for arithmetic sequence. And I guess I sort of tossed out this S sub n. We often use capital S sub n to represent the sum of the first n terms of a sequence. So, and that's often called a partial sum. It's called the nth partial sum. Partial sum because it's finite, and the sums we're going to be interested in are infinite. So this is called a partial sum. All right. All of this is summarized in the sheet that I gave you here. here are some of the notations we talked about for a sub n, the definition we talked about. We're going to talk about limits coming up. Arithmetic sequence is your arithmetic sequence formula. This is called a recursive definition. This is an explicit definition. Geometric sequence, recursive and explicit. Some of the first n terms of a sequence, we can denote it with a summation instead of s sub n. S sub n represents the summation from, I used k here, some people use I, k equals 1 to n of a sub k, because we have to use n for the number of terms we're adding. So we need another index variable like k or I to keep track of which term we're on. All right, and then here's our partial sum formulas for arithmetic sequence. Right there, this is where we are at here. Boom, right, that's where we're at. So next, we're going to show why this is true. This is very astounding, and the derivation of it, like you may have seen the derivation. Hopefully your pre-calculus teacher will have showed you where this come from. If you have not seen it or you don't remember it, it's really a very nice piece of mathematical reasoning to get this formula. And also, this is the one, being geometric, that's going to like really be of great interest to us as we go forward into infinite sums. So that's what we're going to do next.